Good morning, everyone. My name is Ayushi. My today's topic is chemoosmosis coupling. And first, I will talk about the aerobic respiration. Aerobic respiration. What is aerobic respiration? It occurs within the cell. It starts with the glycolysis in the cytosol of the cell. It then goes through the link reaction, moving into the matrix of the mitochondria. It then goes through the citric acid cycle within the mitochondrial matrix. Then it goes through the electron transport chain and chemiosmosis in the inner mitochondrial membrane, producing energy in the form of what? In the form of ATP. In this video, we are going to look at the fifth and the final process that is involved in the aerobic respiration, chemoosmosis. Chemiosmosis. Chemiosmosis occurs in the inner mitochondrial membrane and is coupled with the electron transport chain. It occurs through an additional membrane protein called ATP synthase, which, as the name suggests, is involved in the production of ATP. ATP synthase is a rotating molecular motor consisting of F0 subunit, which consist which consist of the rotating rotor that sits in the inner mitochondrial membranes and the stator which is anchored in the inner mitochondrial membrane. ATP synthase also has a F1 subunit composed of the internal rod that also rotates and the catalytic knobs. At the end of the electron transport chain, we were left with a hydrogen concentration gradient with a higher gradient in the intermembrane space compared to the mitochondrial matrix. The hydrogen H plus protons are higher concentration in the inner membrane and then they to move down their concentration gradient into the lower concentrated area of the matrix. These hydrogen protons moves through a channel in the stator of the ATP synthase. Once they exit the channel, they bind then on the rotor, and this binding causes a change in the shape of the rotor subunit, which in turn causes the rotor to rotate within the membrane. Once the H plus makes complete rotation, it moves through a second channel in the stator, then leads to the matrix. The catalytic knob consists of several subunits, including three catalytic subunits that can be found in the three different states: ADP and phosphate binding state, and ATP state, and the releasing state of the ATP. ADP and the phosphate, the movement of the rotor also causes the internal rod to rotate, which cause these catalytic sites in the knob to activate. The movement of the internal rod causes the shape of the subunit to change and forces ADP and the phosphate already in a bound active state to join and create a new ATP molecule that is bound in the active state. In this active state, as this internal rod continue to rotate and change the structure of the knob subunit, the ATP is released is able to bind more ADP and the phosphate. Oxidative phosphorylation is the process that occurs on the inner mitochondrial membrane to produce energy in the form of ATP. It involves both processes of the electron transport change in the oxidation of the NADH and FADH2 to produce a proton concentration gradient, and also chemiosmosis where the ATP synthase is powered by this gradient to form ATP. Now that we have ATP being produced, what we really want to know is how much ATP is produced in aerobic respiration for each molecule of the glucose that initially enters glycolysis. During aerobic respiration, we get 2 ATP directly from the glycolysis, 2 from the citric acid cycle. This gives us 4 ATP and total of 10 NADH and 2 FADH2 that go into the electron transport chain. For each NADH that goes into the electron transport chain, passing on its 2 electron, 4H plus are pumped in the complex 1, 4H plus in the complex 3rd, and 2 plus in complex 4th, giving a total of 10 H plus proton pumped for each NADH molecule. For each FADH2 that goes into the electron transport chain, passing on its 2 electron, 4H plus are pumped through a complex 3rd and 2H plus at the complex 4th, giving a total of the 6H plus pumped for each FADH2 molecule. But how many ATP are produced for each NADH and FADH2? This number varies and relates to the number of the subunits of the rotor. In each rotation of the rotor on the ATP synthase, 3 ATP are made in the catalytic knob. The amount of the H plus needed to produce a molecule of ATP depends on the number of subunits on the F zero rotor. This number varies depending on the species of the ATP synthase is found in, but usually somewhere between 8 and 15. If it has 9 subunit, it will take 9H plus to rotate once and produce 3 ATP, which equates to 3H plus to make a single ATP. A hydrogen H plus is also used in the ATP ADP translocase to get ATP out of the matrix, raising the number to 4H plus per ATP molecule. In this scenario, for every NADH with 10H plus protein pumped, it's 2.5 ATP, and for every FADS2 with 6H plus pumped, it's 1.5 ATP. So for 10 molecule of NADH, you would get 25 ATP, and 2 molecule FADH2 would give what? It will give 3 ATP plus the produce 2 in the glycolysis and 2 in the citric acid cycle. We will get a total of 32 ATP per molecule of the glucose. Many calculation round up the estimate of ATP to 3 ATP for each NADH and 2 ATP for FADH. For each FADH2, which would give a total of the 30 ATP from NADH, 4 from FADH2 plus the 2 from the glycolysis and 2 from the citric acid cycle, giving a total of 38 ATP for each molecule of glucose. That